Ever wonder what's really inside your smartphone? Today, we're going to uncover a hidden chemical challenge, how we separate two nearly identical elements that are absolutely crucial for the tech we use every single day. Let's get into it.
So let me ask you a question. Imagine you've got a pair of identical twins. They look the same, they act the same, they even respond to things in the exact same way. How in the world would you tell them apart? That's pretty much the exact challenge chemists face with two very special rare earth elements.
Meet holmium and erbium. In the world of chemistry, these guys are basically doppelgangers. They're found all tangled up together in the same rocks, like monazite, and here's the kicker, they react to almost everything in the exact same way. This makes pulling them apart one of the biggest headaches in material science.
But someone did manage to separate them, long before we had fancy modern labs. So to understand how, let's take a trip back in time, back to the 19th century, and meet the scientists who first realized these twins weren't really twins at all.
The year is 1879, and our hero is a Swedish chemist named Per Theodor Cleve. Now, he was working with a substance that everyone, and I mean everyone, believed was a single element. But he just had this hunch, a feeling that there was more to the story.
Cleve used a method called fractional crystallization, which, let me tell you, was a true test of patience. He would dissolve the material, wait for little crystals to form, and then do it all over again, and again, and again. He was betting on this tiny, almost unnoticeable difference in how fast the two elements would crystallize. This was just incredibly painstaking work.
And here's the payoff. After all that effort, he had two totally distinct powders in front of him. A really vibrant pink one that was erbium oxide, and an earthy brown one, which he named holmium oxide. I mean, just through sheer persistence, he had proven they were two completely different elements. Amazing.
Okay, so Cleve's method gave us grams of this stuff, but our modern world, we need tons. So how did we leap from his little lab bench to the massive industrial processes that power our lives today?
Well, it all starts with a big old rock. First up is beneficiation, which is just a fancy word for giant machines crushing and milling the ore into a fine powder. Then comes leaching. That powder gets dissolved in hot, strong acid, which turns all the solid rare earths into this kind of liquid soup of salts. And, very conveniently, this step also gets rid of some nasty radioactive impurities like thorium.
Now for the main event, solvent extraction. This is the heart and soul of the modern process. The basic idea is actually pretty simple. You take two liquids that don't mix, just like oil and water, and you use one of them to selectively snatch the element you want, leaving the other one behind.
But how do you make that snatch selective, right? How do you tell the solvent, hey, grab the holmium twin, but leave the erbium twin alone? Well, the secret, it's all about controlling one simple but incredibly powerful variable.
And that variable is pH, the acidity level. You can honestly think of it as the master control knob for this whole separation. By tweaking the acidity just right, chemists can change how strongly each element is attracted to that oily solvent. It gives them this incredible, precise control.
So here's how it works. You dial in one very specific, very carefully calibrated pH level. At that exact point, an organic solvent like P507 basically turns into a selective magnet. It suddenly develops this powerful attraction specifically for holmium, and it starts pulling it out of the watery acid solution.
And just like that, the separation happens. The holmium literally jumps into the oily solvent, while the erbium, which isn't affected at that particular pH, just gets left behind in the water. After doing this over and over again through hundreds of stages, the twins are finally truly separated on a massive industrial scale.
But we're not quite done. We still have to get that holmium back out of the solvent, right? That's a step called stripping, where another acid wash pulls it back into a water solution. Then we use precipitation to turn that liquid into a solid. And finally, calcination, which is basically just baking it at super high heat, to get that pure brown holmium oxide powder that Cleve first discovered.
Just look at this comparison. It really puts the progress into perspective, doesn't it? Cleve's method took ages, maybe years, to produce a few grams of sorta pure material. Today, we can churn out tons of extremely pure holmium and erbium in a matter of hours. It is an absolutely incredible technological leap.
So why go through all this trouble? Why does separating these chemical twins matter so much? Well, the answer is probably sitting in your hand right now.
All right, let's recap this whole journey.
We started with holmium and erbium, these chemical twins that are super difficult to separate. We saw how Peyote Cleve first did it, slowly, by hand. Then we saw how modern industry uses this massive-scale solvent extraction, and we learned the secret key to the whole thing is that precise pH control, which unlocks these amazing elements for all our technology.
So next time you use a piece of high-tech gear, just remember those pink and brown powders and the incredible chemistry that pulls them apart from a simple rock. It really makes you wonder, doesn't it? What other invisible elements are hiding in the technology you use every single day?